before tomorrow presentation and the experiment this afternoon, the demonstration this afternoon.
Please do not hesitate here.
Talking about NV centers, one of the main problems is scaling it into a large scale. Where are all the issues in making multiple copies of the system? Like, where do we face on that?
Mainly, there's two issues, I would say. It's mainly due to the conversion yield. You can do implantation. You can even do what's called deterministic implantation. That means that you are able to have an ion beam machine that can provide only one ion at a time. And there are two ways to do that. The first one is somehow you control that you have a clever electronics that somehow when the ion pass and you are very, so basically what you have is you make a very dim ion beam with very, very low flux. So within a given time, you might have only one ion. Most of the time you will have no one. But nevertheless, you still have a probability, because it's Poissonian, it's Poisson distribution, that having two ions. And that may be something you don't want, because you want to have one and one and one. And so for that, there's one option that was designed and developed, currently developed by Jan Meyer, but it's quite difficult. Is to have a clever electronics where basically you are able to detect one charge, and or two charge, and if you detect two charge, then you block the beam. Okay, you have fast shutter and you block the beam. So this is one possibility. The other possibility to start from a real single atom source, and that people know. For instance, we know how to trap a single ion. And so using that, you trap a single ion. Usually, for instance, it's calcium or those kind of ions. And then with some exchange, you're able to trap one nitrogen. And then you shoot the nitrogen after that. And because you know that there is only one ion in the trap from the very beginning, you know that you will get only one ion at the end. So this is very nice also. But the problem with that is after that, the accuracy of the focusing remains a problem, because somehow it's still challenging. So the other problem is the yield. The yield is very low. So it means that somehow you can say, okay, I repeat until I know that I have got implantation of one, which is one possibility perhaps. So there's people working on that really hard. There's one company in Australia, founded in Australia, and that a subsidiary company in Germany, which is called Quantum Brilliance, and that is really trying to develop this approach. There's another company also in Germany, and I think up to now they have succeeded in having a few ions, NV centers coupled, but this remains very challenging. And the accuracy of the beam somehow you can go down to 10 nanometers. So 10 nanometers would be, this is a little bit too far from getting dipolar coupling within the T2 star. You can do it within the T2 somehow, that's okay. With the line width will be smaller. But okay, that's why it's mainly a problem of being able to build such array of NV centers in which you're sure that you can address them. There's another problem also, it's the charge stability. Because if you now put two NV minus very close to each other, what happens to the charge? You have two charged ions somehow very close nearby. Will it remain stable within the solid state environment? This is not clear also. So it has been, people that do those experiments, they found very easily two pairs of NV, a pair of two NVs. For instance, you implant two, even by simply implantation of N2. You implant N2, the 2N2 will break, the molecule will break when the two atoms enter in the lattice, and then we'll have one N. By annealing, you will get something like 1/1000 pairs. So if you have systematic raster scanning some system or whatever, you find them. Either you do it by hand, it's a little bit boring, or you simply you build a machine that can explore automatically that, and you find a pair. So this is not too difficult. There's no experiment up to now, to my knowledge, had been reported with 3. So that's a little bit the difficulty. And after that, there's again another problem, because how do you address them? We've seen that all the addressing is done based on optical means. So you can say, okay, they will be detuned somehow, and I address them by different frequencies. But then when you have now 3 of them, then it becomes again more and more complicated. So somehow what the competition with Rydberg atoms in tweezers, to my point of view, is very hard at the moment, because in optical atoms in tweezers, you have now these atoms that can be very well separated in a way that each of them can be independently addressed by sort of confocal microscopy, and they interact through the dipolar interaction associated to the Rydberg state. So it's quite hard to beat that, to beat atom in tweezers. So I don't know. I think it's maybe where there are a strong interest could be, for instance, for simulation, because then you have a register and you have this long-living nuclear spin, especially if you're at low temperature, and you can maybe have those kind of things. The other possibility that people are exploring, not with NV, but more with silicon vacancy center, is to have now pure, very good single photon emission, and after that you untangle the system by coalescence of the single photon that are emitted. You mix them on a beam splitter, and that will untangle the two atoms, and you can also now address independently a nuclear transition, for instance, associated to these silicon vacancy centers, a little bit like what we do it. But then it's another approach. The thing that is needed then is very efficient platform where you are sure that you couple very efficiently single photons in and out a single SIV center, for instance. And so it relies on development of diamond nanophotonics.
Would NV centers be used to test fundamental quantum physics or some test fundamental theories? Is there some thought going on in that?
What do you mean by fundamental?
Like for example, well, I read somewhere that they've been using trapped ions to test general relativity.
Ah.
Some experiments like tabletop experiments.
I don't know. maybe, I don't know. I have no idea about what can be done with that. There are people that want to try, for instance, to trap nanodiamonds and investigate the physics of and being able after that to cool it down. And so for that, you can use, for instance, if you have a gradient magnetic field, you have the spin inside the trap, and somehow, if you can monitor the position or the motion of the NV in the trap by some kind of addressing the system, perhaps you can imagine to cool it down, again to cool it down to the first level of an harmonic oscillator, and try to see what happens in that case. For instance, you have a macroscopic nanodiamond, and then you want to slide to change it in position and see it might change. That could be one possibility. I think again you have to see whether or not it competes with other systems that people are investigating, and the efficiency of cooling them using nanophotonic nano mechanical oscillator and those kind of things. So I'm not sure that somehow this is really where you have the main advantage for that. Yes? A diamond transistor. Yeah. I can prepare. It should be, I'll come back to that. Puff, puff. It's associated to that, to PDMR detection. I mean, at one point, all the information you have with optical ODMR and the sensitivity of any sensing scheme relying on ODMR will depend on the contrast. And the contrast is somehow, let me write it down. Let me see. Okay. Okay, I just wanted to make, I don't know, let me see. Okay. Good. I will try to write it down. So basically, the contrast is like that. Okay. This is what I will call the contrast. And then you can convince yourself easily that the sensitivity of all my measurements will be directly related to the contrast. If I have a weak contrast, of course, I won't be able to detect something, especially because here it will be a noisy signal somehow. I'm putting like that. And the noise will be just the photon noise. You register a given number of photons, n photons during your measurements. So you have a noise, the shot noise associated, which is square root of n photons, okay? And then the other parameter important is the contrast. So that's somehow the main parameter for the two things. Suppose now that I have a balance of NV minus and NV0. Then the NV0, what does it will do? It will just add parasitic luminescence. So if I have this effect, so suppose this I have only NV minus, and now I plot the same now with NV minus and NV0. You already found what I want to say. I will have the same contrast, the same depth here, but now with NV minus plus NV0 background. Okay? And it means that somehow my contrast is significantly reduced. So the problem of all that is that it's somehow quite hard. Anything that brings parasitic fluorescence will somehow decrease the contrast value and will directly impact the sensitivity. On the PDMR, for the moment, if we look back to the PDMR, it should be here, that we have here. Of course, we see it it's like this curve. We see it really like there is a contrast. But the contrast it seems to be much higher. This we do not understand. But somehow you can find trick where basically you would eliminate this value. Okay? And if you eliminate this value, then you have a signal which is now over 0. So, and it's completely different way to measure, to evaluate the sensitivity in that case. So this is why actually you can play with different electrodes to have somehow basically a kind of system where depending on, you can imagine to have like a transistor. A transistor is exactly like that. It's something that would rectify, that is based on PN junction, but associated in a way where one controls the other one. So you may find things like that. So what I'm just saying is that those kind of geometry associated to the photoelectric detection opens a lot of possibilities. And this is just something that I think is worth exploring. Sorry, what's the electrode here? So it's just graphite. So basically, and that's the point is that somehow it eliminates the need somehow to have the carbide bounding between the diamond and the metallic electrode you want to detect. So just by carbon, you do implantation, or you could also write them with laser. So you could even imagine having those graphitic electrodes buried really inside the diamond, and then connect it through channels to the outside where you would have a real package. So there's a lot of, again, possibilities associated to that. And actually, it's also nice because you don't need any, if you have a machine or any device that can do the implantation, you do not rely on complex system for getting these electrodes. And you can do channels, you can do, you can imagine playing with many geometries for those electrodes. You could also imagine having like electrodes, like one that could be somehow a kind of field effect, something very tiny, and another electrode that would collect all the charge. So there's a lot of possibilities associated to that. And that's what my colleague in Thales are currently exploring. Yes? Yes, indeed, yes. Good point. Maybe we discuss that with one of the paper tomorrow. If you are perfectly aligned on the magnetic field, there's no problem. You keep the symmetry, and then you can be up to in the Tesla range, 0.5 Tesla. What you need is to accommodate for the frequency will get higher and higher. But apart from that, there's no. As soon as your magnetic field is perfectly aligned, that will be. There's no problem. You keep the basis, the good basis state. Now, as soon as there is a transverse component, and this will be discussed in one of the paper I propose for tomorrow, then that will mix up the state. And the mixing of the state, of course, will have drastic consequence on the contrast of the magnetic resonance. And somehow if I come back to what I said, what we will show then is that if I plot stupid. Okay, let's come back. So let me write this. I remove that. Okay, and you will see that somehow the contrast. Let's see it, but it's in the paper we're going to discuss tomorrow. If I put, for instance, a component B, which is perpendicular, I have a curve that will be like that. Okay, and this is a value around, let's say, 10 millitesla, and this is C optimal, where B is B perpendicular, only a magnetic field. Of course, you have to take into account a reasonable value of B parallel, so it's a kind of compromise, but let's put just you just tilt, for instance, B perpendicular, for instance, at a given angle, and then you'll see some behavior like that. So as soon as you have a transverse component rather strong, somehow this induces some problem. But that can be also an advantage, as this will be also discussed in the paper, because this transverse field will shorten the T1. So if you do a T1 measurement, then you can access the existence of a perpendicular field. And somehow this has been developed to map transverse magnetic field. So for instance, you imagine the scanning NV system, and with the scanning NV system, as soon as you have a transverse field, the T1 is very short. And the consequence associated to a short T1 is that the intensity of luminescence of the NV will be drastically modified, will be much shorter also. So just by looking at the brightness of the emitter, you can see whether or not there is the existence of a strong transverse field. It's hardly quantitative. It can be a little bit quantitative, but the good point, if you just do a mapping and you want to measure, for instance, a domain wall associated to a magnetization that goes from that to that, there will be a transverse magnetization at that point, and this transverse magnetization can induce this, you can observe it. So somehow you can observe domain wall in which the system, the magnetic field is in plane, for instance. Those kind of things. So there's really a lot of interest in applying this technique, even for getting simple image of magnetic textures by scanning NV magnetometry. But now, regarding your question, there's no limit of the magnetic field, providing the 2 points, providing one that you have the microwave equipment to go up to very high field, to a very high frequency, and the other one that you're aligned on one NV family. Or you work, for instance, with 111 samples on which you know that you have those kind of things. There's two important, basically we can work with different orientation. One is 100, so we have this 4 family. Most of the experiment I show you were based on this 100 distribution, orientation. You can work with 111, then you have one family which is pointing up the sample, upward the sample surface. And then you can work also with 110. And this is quite nice because then you have 2 families of NV that are in plane. And this is quite nice because now you can apply a magnetic field along one of those directions and observe now, apply a very strong magnetic field in this direction, which is also very nice. And for instance, also tomorrow we'll discuss that perhaps in one of the paper for radio frequency analysis. Spectrum, the NV spectrum analyzer, people use this configuration.
And is there any direction there where we can see no effect of magnetic field on the system?
No. No. No, there will always be an effect. No. Maybe I guess you will always have, yes. Maybe, yeah. Thank you. Yes?
You mentioned once that NV's implementation will take too many sessions.
Yes.
But you also mentioned that it was not scalable.
Yes.
What was the reason that you said?
The reason is really the conversion yield, mainly I would say. If I would be able to convert any nitrogen implanted to an NV center, that would be really fantastic. But the problem somehow is that the conversion yield is limited. And it's limited due to the point that I can just show you that. If I, not very useful. If I have okay, just suppose now I implant an atom, okay? This is the beam, and the implantation usually lead to a distribution like that of the atom. So you don't know where they are within this kind of pear-shaped distribution. And the distance here will depend on the energy here. So if I have, for instance, an energy of 30 kilo electron volt, which is often what we use, usually we implant N2 molecules. It means that each molecule will dissociate. So and each atom will get half of the energy. So it's an effective implantation energy of 15 kilo electron volts. And if you do some simulation about that, you would say that this is a depth of about 10 nanometer. When we have that situation, I'm sorry, we nevertheless have one atom. This is the nitrogen. And all around there are vacancies. These are the vacancies, okay? And when the atom stops, it creates a lot of vacancies. And even more vacancy, of course, If the energy is high, is very high, then you create lot of vacancy. The problem now is when you anneal, all those vacancy will move, but most of them will actually go to the surface if you are close to that. So, and once they are at the surface, they are trapped. So you have a kind of balance. Either you do at low energy, but at low energy, recombination with vacancy will be mostly inefficient, which lead to a very low yield, only below 1%. So, okay, you can say I retry, but most of the vacancy will go to the surface, unfortunately. Because then what I would like to have, for instance, is 2 nitrogen like that. And these 2 nitrogen, if I want to get them very close, I need very small energy here. Okay, so basically you have this problem. So what you can say, okay, no, not a problem. I do this, and now I do the overgrowth of a diamond layer. They are really far now from the surface, and I still can create a lot of vacancies by electron irradiation, things like that. And then they will be really buried. And once they are buried, the recombination rate is enhanced, of course, because you are far from the surface. Okay, and that has been demonstrated. The conversion yield increases when you implant deep in the diamond. But if you do that, of course, you lose the accuracy. So a way to beat them would be we do shallow implantation, and then you go to a CVD reactor, you reimplant a pristine layer of diamond, and you redo the electron irradiation to create vacancy, and you see if you indeed achieve the yield. It could work, but there's a lot of technical issues. It's always, at one point, you need some kind of engineers that are really working hard to optimize all the process. Why? Because, for instance, we tried that experiment. So we prepared a very, very nice sample. We took us a lot of time to investigate where the NV was, to make a kind of pattern and all that, with very weak energy. So we are very high. It was a month of work of preparing that. Then we sent it to people that were able to do the overgrowth, to grow and get of them. And then they said that, okay, come on, look, we are very sorry, but your NV layer has disappeared. And the reason why, when they put it in the CVD reactor, they turned on the plasma etched the diamond surface, and it was completely removed by just the etching with the plasma. So you have those kind of stupid things that happen. Again, it doesn't mean that it's impossible. It just means that at one point you need people to have a kind of technological development that believe somehow in the outcome, and that can work reliably for 1-2 years, focusing on addressing these issues. And at one point, whether or not you are interested to doing that, that's the question always. And up to now, well, no one really did that. Because they are, at the end, you compete with other platforms. And if with the other platforms are more efficient, I hope it answered your question. It's a matter of competition, to my point of view. I'm not saying it's impossible at all. I'm just saying the effort that is needed is significant, and after that, we realize that you need very specific CVD reactor to be able to do this overgrowth on top of such samples. There is people in Germany that spend years now to develop this very specific CVD reactor that allows such overgrowth in Freiburg, at the Fraunhofer Institute in Freiburg. So perhaps they will definitely be able to grow things a little bit like that and have NV close to each other in a very pristine diamond environment, far from the surface, which is a source of endless problem. So that's the point. Yes, please. Sorry, two? Okay. So I have two options. If I want to make, I ask you, you ask me, please do a gate in diamond. I have two options to follow. Maybe I can prepare two slides like that for tomorrow. The first one is we have two NV, okay? And we rely on the dipolar coupling with each other. And the dipolar coupling, we create now a little bit like what we said with the mixing of the state. We will have, instead of having the same resonance, they will split in a doublet. And I need now to address this doublet. Okay? There is nevertheless a problem, because somehow you've seen all the readout that we have is somehow done with the NV by shining light. And if the two NV are close to each other, then it's very hard to address one and not the other, because they will be too close. So as soon as I put light, I reset everything. I reproject, everything is pumped into MS equals 0. So then somehow you have a problem of how to, you will identify the dipolar coupling, but now how can you read one qubit and not the other one, for instance? This is difficult. So you have those kind of issues just by light. Now what is more efficient somehow is you have the NV and you have a CNOT gate. You have the carbon 12, the carbon, it can be already the carbon 14 that we have embedded with the system, or you have a carbon 13. And so you play now with the system. And this happens to be quite efficient. Again, the problem is you will build a very nice 2-qubit gate, like a CNOT gate, and basically now all your readout spin is the one that is the NV, electronic spin. So but the light which is there cannot, somehow you can design a scheme where it has no influence on the nuclear spin. And this is nice, to be honest. You can even now play after that, addressing one NV to two carbon 13. So you can play with those kind of things. And unfortunately, this is, again, not scalable. So I can say I have a nice system that able to couple to long-lived nuclear spin resources. But now the question is how I make that scalable. And you can say, for instance, which is interesting somehow, that's the way people, perhaps the most promising path at the moment, is somehow to use single photons from the NV and coupling to carbon 13. And now you use these single photons, for instance, to couple to other NV centers. So then you can have architectures like that. So I would have one diamond here in which I would have one single NV, one carbon, one nuclear spin acting as a resource, and then I can store the information in the nuclear spin if I want, or I can retrieve it. Another one, and then I untangle the two systems by mixing them. This works. It has already been developed, for instance, by people in Delft, in the team of Ronald Hansen, and made a test of Bell inequalities without a loophole-free test of Bell inequality using that. But it works. Unfortunately, it's again the problem of getting single photon, indistinguishable single photon from a single NV, which is difficult due to the poor rate of emission in the zero phonon line. So another way, more efficient to implement that, is to use, to look at a single vacancy center. They have narrow emission if you put them at a few Kelvin, and then you can hope with them to have indistinguishable photons and also to couple them to cavities, to things like that. So we're closer to system to what people are doing in quantum dots. So the advantage, I think at that time, you compare with quantum dots. Quantum dots, people know very well how to store, how to couple their emission to microcavities. And they have beautiful experiment, very efficient single photon source that emit 1, 2, or 3 millions of photons, even more now, per second. One of the problems they have is, for instance, they do not have a very obvious access to nuclear spin in the quantum dot. On the other hand, with diamond, you have very easy access to the nuclear spins. But now the problem is on the other side. You want to couple them to microphotonics to have emission channeled in one direction, and this diamond photonics is quite challenging. So the other possibility now people are exploring is to work on defects similar to the NV that exist, or other defect, a diamond defect, but which exist in silicon carbide. And the advantage of silicon carbide is that it's much easier to do nanophotonics, photonic structures. It's a well-known material from the semiconductor industry. So you have a large wafer, you can do, all the nanofabrication processes are much easier to do in silicon carbide rather than in diamond. Diamond, it's a nightmare materials for any nanophotonics processing. But thanks for this question, because it's really show what all the people are exploring at the moment. And there is definitely not a single platform that one can say it will be the other one. Yes?
So in some of the heat-spin polarization nuclear spins, we carry the coupling between the electronic states and the nuclear states,
Yes?
only because nuclear spin states have a higher coherence mass.
Yes.
That is the reason to map the quantum state from the electronic spin to the nuclear spin.
Yes.
But won't it affect the state itself, low fidelity efficiency?
You mean for what? For a gate or?
For storage, quantum state storage.
Let me think if there were. I think there were experiments where people tried to do that and reach very high fidelity. But the kind of thing that we want to do in our case is not for that purpose. So I'm not able to answer very nicely to this question. The purpose for which we are trying to investigate, I cannot answer the question, to be honest. And our interest is a little bit different. The interest for us, let me see, I can perhaps show it here. Yeah, it should be this way. Yeah, no, sorry. Okay, it's arrived. Yes, it's to make a gyroscope, to try to make a gyroscope. There was a beautiful experiment a few years ago where people tried to observe, basically if you have a magnetometer, you actually have at the same time gyroscopes. And the reason for that is if you have now, you will, a gyroscope, something that you want to be sensitive to a rotation, okay? So what happens now, suppose you have a fixed magnetic field and you turn the sample turns. Then the Larmor frequency will be different just due to the combination of of speed. And that means that the spin will turn at different speed. So somehow that will induce a dephasing. So if I do now, suppose I do a Ramsey fringe experiment, I turn the system, that will induce a dephasing. And since the Ramsey fringe are very sensitive, I can measure very small rotation of my sample. And then I have a gyroscopes. And this is something that has been implanted using atoms. And now there is these systems that are done in the US by Northman Grutman. You see the size, and basically it's a cold atom. And not a cold atom, just an atomic vapor. And you look to the precession of the spin of that. And you see the size. But that has been, it was a 30-year time development to achieve that. And you cannot purchase that, so it's impossible. No, so the question is, can you do it with a solid-state platform using NV? There is integrability prospects. It can work also under extreme condition. One point also is there's no warm-up compared to the system. Okay, you may ask yourself. So our thing is that, but then the important point is, of course, you want to see the dephasing. But the dephasing with the rotation, the angle, will be depend on, of course, the time that you can have for your measurements. And the time you can have for your measurements is a T2 star. All experiments are limited by T2 star. So if I take electronic spin, as I show you, the T2 star is about microsecond. If I take a very nice sample, but that would going to be very expensive, I can reach even a little bit more. So the question is, can you design a scheme that relies now on the nuclear spin? The nuclear spin, as I will show you, they have a T2 star, which is in the millisecond range immediately. And they can be even higher somehow if we happen to engineer the material. So that's the idea. That's why we were interested in this question. It was not somehow about using that, so unfortunately I don't know the answer to your question, but I think the fidelity was quite good about information in, information out. But now comparing to other systems, I cannot benchmark. Okay, if you have any other questions. Good. So we meet again at 2 o'clock for the, no, 2. For my colleague, it's better at 2. So if we can, we just be, and we start with a 2 demo experiment, and hope so. Then I will launch the Zoom a little bit before, and so that to see if everything is in order. Thank you.